So I'm just going to give a review talk about primordial non-Gaussianity. I'll talk about the theory, cosmic microwave background constraints, and future prospects for large-scale structure. So first off, to briefly introduce the parameter space that we're trying to constrain. If we start by considering single-field slow-roll inflation with a canonical kinetic term and a nearly flat potential, then as everyone here probably knows, quantum mechanics in a curved spacetime predicts that if we start with all modes in their vacuum state, then we generate fluctuations in the scalar field phi at the end of inflation with a roughly scale invariant power spectrum. And this is what we need for consistency with a large amount of cosmological data. It's been shown in seminal papers by Maldacena and others that in this model, the curvature perturbation at the end of inflation is Gaussian at a level of approximation which is good enough for even very futuristic experiments. This calculation assumes details of this model, the standard kinetic term being minimal coupling, no self-interactions with the inflaton beyond those that are implicitly contained in V of phi, and finally that there's no second field that's important for generating the curvature perturbation, that perturbations in the curvature are generated by perturbations in the same field that dominates the stress energy during inflation. So as I'll review briefly, deviations from any of these assumptions generate non-Gaussianity. So the simplest non-Gaussian model that one might consider, in my view, is this modulated reheating model. Imagine that there's a spectator field during inflation sigma, and that perturbations in sigma are generated by the standard quantum mechanical mechanism, and that those perturbations control the inflaton decay rate. So to be general, I've written the inflaton decay rate gamma as a general nonlinear function of the spectator field sigma. Perturbations in the decay rate generate curvature perturbations because different regions get to expand more or less before the inflaton decays. In general, zeta is a nonlinear function of gamma, but if I plug a general nonlinear function into a fixed nonlinear function, I get an arbitrary nonlinear function with different coefficients. And then if I just change variables and call the combination A delta sigma zeta g, this is some Gaussian lowest order approximation to zeta. Zeta is non-Gaussian. It's given by a zeroth order Gaussian piece, plus a correction which is proportional to the square of that same field, where the coefficient f and l here is a free parameter that we would like to constrain. So I've motivated this new parameter f and l by this modulated reheating model, but the model is more general than this specific mechanism and generically arises in multi-field models. Local non-Gaussianity. I'm going to classify non-Gaussianity into local and non-local types. When I say local non-Gaussianity, I mean the parameter space with these three parameters. I've already defined f and l. G and L is, if I want to constrain f and l, if you imagine that I'm constraining, if I observe, say, all modes of the curvature perturbation in some 3D box, then to lowest order in f and l, the way that I see it is by measuring the 3-point correlation function, which is easy to compute. And if you work out where the signal to noise comes from for constraining this 3-point function from observations of the field, putting in all the correct phase space factors and so on, you will find that most of the signal to noise comes from these so-called squeezed triangles, which will play an important role throughout the talk. The GNL model is the same thing with the cube here instead of the square. By the zeta g to minus zeta g symmetry implies that all odd cumulants of this guy vanish. And so to see GNL, we have to look at the 4-point function. A similar signal-to-noise calculation shows that most signal-to-noise comes from these so-called squeezed quadrilaterals, where one of the k's is much smaller than the other three. Finally, tau and L is perhaps a little more awkward to define, but it's defined as follows. If we go back to the f and l model, then there would also be a 4-point function at order f and l squared. And if we allow the coefficient of this 4-point function to be an independent parameter, tau and l, not necessarily equal to the square of f and l, then we get what's called the tau and l model. So tau and l, by definition, is just the coefficient of the 4-point function, assuming that it has this shape. In the simplest case, it's equal to f and l squared, or rather 6/5 f and l squared is the conventional normalization. So tau and L, by definition, to show you where it comes from, by definition, it's in the 4-point function. And it turns out to come from these collapsed quadrilaterals, which are sort of squeezed in a different sense. The vector sum of 2 of the k's is small compared to any of the 4 k's in the configuration. OK, so that's local non-Gaussianity. There's also, it's fairly simple, it can be described in about 5 minutes. There's also non-local non-Gaussianity, which is more QFT oriented, and it would be a complete talk to survey all the possible shapes that can arise. So I just want to give a representative example. There's this very influential paper by Eva and co-authors proposing dBi inflation, a string-motivated model of inflation, where the inflaton is the distance between 2 branes in a compactification, and non-Gaussianity is generated by this non-standard dBi kinetic term. After a suitable magic change of variables that I'll talk about a little bit on the next slide, you can transform this action into an action that looks like one with a standard kinetic term for the minimally coupled scalar, or with a minimally coupled scalar in the near de Sitter background, plus an interaction term proportional to sigma dot cubed. So this is the piece that generates non-Gaussianity. And we can compute its 3-point function just by the Feynman diagram expansion. In this model with the sigma dot cubed interaction, there's just an easy tree-level QFT calculation that gives you the 3-point function. So if we want to constrain dBi inflation, we're looking for a 3-point function with this k dependence and a coefficient f, which is a new parameter. When you forecast signal to noise for this shape of the 3-point function, it's peaked on equilateral, roughly equilateral triangles. And so this signal is quite different from the FNL signal that I talked about previously. The cosmologist's name for this 3-point signal is FNL equilateral. OK, so that's a simple example. I could go on to tell you about a lot, many more examples that have the flavor of adding, say, a cubic interaction if we want a 3-point function, or a 4-point interaction if we want a 4-point function, to the standard kinetic Lagrangian. Physicists are very good at, if you give them a quadratic action, of thinking up all sorts of interesting interaction terms to add. So I listed a few of them, my personal favorites on this slide. I won't talk about them in much detail. One comment I would like to make is that the philosophy here is very similar to particle physics, where we just write down all interactions that are consistent with a given set of symmetries, the relevant symmetry in this case being the approximate time translation that allows inflation to last for many e-foldings, and then just constrain all of their coefficients as independent parameters. OK. One more comment. So I said that pi dot cube generated what's called FNL equilateral. I'm also going to talk about this operator, which generates a shape which is nearly identical, but not exactly the same. So there's some linear combination of these two leading order cubic interactions, which is what we call the orthogonal shape, FNL orthogonal. OK, so there's a 2-parameter space here, and we can measure 2 parameters and constrain both coefficients. OK. So that was sort of a lightning review of the theory. Let me now talk about the Planck constraints. So I've divided non-Gaussian. So as everyone's heard, I imagine, Planck finds consistency with Gaussian statistics. The main 3 FNL parameters are, the main parameters that are constrained are FNL local, and these parameters FNL equilateral and FNL orthogonal, which correspond after change of variables to the coefficients in this, the cubic operators in this action. In this part of the slide, I've just listed a variety of signals that I've classified by being either 3-point signals or 4-point signals. And then I've further classified into local and non-local shapes. And I've color-coded blue if our Planck paper reports a constraint, and color-coded red if it hasn't been constrained yet. Some of these are my fault. But the point of the slide is that the main parameters that the community is interested in have been constrained, but there are many that have not. The main reason for this being that the 4-point analysis is much more difficult systematics-wise than the 3-point analysis. And so one should think of these results as sort of a work in progress. We're only about halfway done constraining all the shapes that theorists are interested in. Okay. Just to give an example of how these constraints are useful in constraining a particular model space, here are the constraints on the parameters FNL equilateral and FNL orthogonal. These parameters are constructed in such a way that they're roughly uncorrelated, so that you have a roughly circular error ellipse. And if we translate into the parameters of the Lagrangian a sound speed Cs and a free parameter A, then we get, that's a nonlinear transformation, and we get this funny looking region here. The non-Gaussianity parameters give it, robust constraint, more or less robust constraint on the sound speed of the perturbations during inflation. If one chooses a generic value for this parameter A, then you would find, say if we choose A equals 0, then we would find a lower bound on the speed of the fluctuations, which is a few times 10 to the minus 2. And if one allows A to be arbitrary, then you get a more conservative lower bound, close around 10 to the minus 2. This funny looking shape where there's kind of a near degeneracy that's broken is because there's a regime where one can tune the parameter A to nearly cancel these shapes against each other, and the measurement of FNL orthogonal is what breaks the degeneracy down here. Okay. So what do these constraints really imply for our knowledge of the universe? Well, here's my take. We say in the Planck papers that the Planck non-Gaussianity constraints put pressure on certain models. There's a volume of parameter space which is formally reduced. But really, I think it's best to be more conservative and say that it's hard to rule out qualitative classes of models without getting to FNL of order 1. If we had just asked the theory question, roughly what FNL do you need to start differentiating qualitatively between different mechanisms for generating the perturbations, forgetting about how expensive and difficult the experiments are, I think that most of us would have answered that this is roughly the level. So just for example, the Planck FNL local constraint, it reduces the parameter space for a modulated reheating model or what's called the cyclic model, but it doesn't rule those mechanisms out as far as I can tell. There's some interesting exceptions. In UV-complete models, there's often a trade-off between tensors and non-Gaussianity. For example, in EVA's dBi inflation, there's a combination of the tensor-scalar ratio R and FNL equilateral, which has to be above a certain level, such that you can't make both tensors and equilateral non-Gaussianity small at the same time. It looks to me like dBi inflation is still OK with the Planck limits on FNL equilateral and R. But if R were improved, if the R constraint were improved by, say, a factor of 10, then this model the dBi mechanism would presumably be ruled out, or at least require an unappealing amount of fine-tuning. Okay, so it's natural to ask the question, can we ever get to FNL of order 1? And my take is that it's going to be very hard to do this in the CMB. Planck is exhausting all the information in the temperature out to the L's where there's a lot of secondary non-Gaussianity that makes the primordial non-Gaussianity difficult to disentangle. But the answer is possibly yes in large-scale structure. So I want to just do some review of the large-scale structure theory. So I'm running behind on time, so I'm going to skip a few slides. They're just general comments on endpoint functions. And jump to the large-scale structure part. I think that's more interesting. All right, so for purposes of this talk, large-scale structure means the power spectrum on large scales, where the signal that I'm going to be talking about is the following. So let me remind you that in a Gaussian cosmology, fluctuations in the number density of halos or their luminous tracers, like galaxies, are proportional to fluctuations in the matter density with some proportionality factor B, the halo bias. So that if I measure the halo-halo power spectrum by counting galaxies, or the matter-halo power spectrum, say, by correlating galaxies and lensing, then I'm measuring the same thing multiplied by factors of B and B squared. In a non-Gaussian cosmology, there's a very interesting effect, which was really first noticed in 2007. There's a big signal in PMH and PHH kicking in on large scales. And one can write this down by saying that the halo bias is now a function of scale with a term proportional to FNL over k squared that kicks in on large scales. Forecasts using this signal show that large-scale structure can eventually beat our current limits from Planck, beat what we can do in the CMB. So one interpretation of this, I want to describe where this effect comes from. One can think of it in the following way. In an FNL cosmology, the three-point function is large in squeeze triangles. And what that means is that if I have a long wavelength fluctuation, then the power spectrum is correlated. So a local observer in a positive long wavelength fluctuation, they see a different local power spectrum than a local observer in a negative fluctuation. And because the observed halo abundance depends on the local power spectrum, this leads to a new term in the bias, which when you put in the factors of k from the squeezed triangle, goes like 1 over k squared. So one can generalize this calculation to an arbitrary non-Gaussian model as follows. So it's interesting to ask, so that's FNL, but the non-Gaussian parameter space that we constrain from the CMB, say, is much bigger. And so we'd like to know how this generalizes to other non-Gaussian models. So with these collaborators, we've done a general calculation as follows. First we need some model for halos. And a model which is useful in a variety of contexts is the barrier crossing model, where we say, let's model the process of halo formation as follows. Smooth the density field on some scale, which it will be the Lagrangian radius of the halos. And then after the density field has been smoothed, threshold at some cutoff value, and say that regions where the density is above threshold are regions where you find halos, and otherwise the overdensity is not great enough for halos to form. This is a rough model, but it gives qualitatively correct predictions for many things. In particular, in this model, the halo field is a completely specified nonlinear function of the initial curvature. So we can just expand the matter halo power spectrum and halo-halo power spectrum in the initial cumulants of the curvature to determine how these power spectra depend on the initial non-Gaussian statistics. And when this is done, one gets a big expression that can be schematically written as follows. The matter halo power spectrum, so this factor is what we would think of as the bias, is a sum of terms where in the nth term, I integrate the cumulant over the endpoint function over configurations where one of the scales is large, or a small k. This scale is the large scale where I evaluate the power spectrum. And the other scales are just broadly integrated over a range of large k or small k's, roughly matched to the size of the halos. The halo-halo power spectrum includes these terms, plus some new terms that correspond to integrating collapsed configurations, integrating an m plus n point function over the set of configurations where the vector sum of m of the k's matches the large scale where we're computing the power spectrum. And so then, armed with this general expression, we can go through some examples. I'll just go through them quickly. For GNL, we find that this squeeze 4-point function generates a clustering signal which is very similar to FNL. In fact, nearly degenerate, and it's hard to tell the difference. So there's a signal, but you don't know whether you've seen FNL or GNL. Something qualitatively new happens in the tau-NL model. One finds that the bias factor appearing in PMH is no longer, sorry, the bias factor appearing in PHH is no longer the square of the bias factor appearing in PMH. This means that the matter and halo fields are no longer 100% correlated on large scales. I don't think this is a very good term, but this is what's called stochastic halo bias in the literature. Anyway, so you can tell the difference between tau-NL and FNL by looking for, by asking whether, if you see this large-scale signal, by asking whether the bias is stochastic. That can be determined by measuring multiple tracers or independently measuring matter fields and matter and halo fields, or even with a single tracer by trying to constrain the coefficient of 1 over k squared and the coefficient of 1 over k to the fourth independently. Another example, quasi-single field inflation. Well, I won't say much about this model, but what's interesting about it for large-scale structure is that first off, it has the stochastic bias. In fact, the stochastic bias is, the bias is mostly stochastic in the sense that the correlation coefficient is close to 0 between the matter and halo fields on large scales. And second, that the 1 over k squared is generalized to an arbitrary exponent, which is related to the mass and Hubble units of a field during inflation. And so the large-scale structure signal, in addition to looking for stochasticity, one should also look at this exponent of 1 over k, which is telling you something new and interesting. OK, so just to conclude, large-scale structure is not sensitive to all non-Gaussian models, only to those that have large squeeze and collapse limits. For example, FNL equilateral is difficult to constrain using this large-scale bias, large-scale clustering approach. Possibly there are other large-scale structure observables that would be sensitive to FNL equilateral, and that's a very interesting thing to think about. Now there are theorems that say that these endpoint functions, the squeeze and collapse configurations, are unobservably small in all single-field models of inflation. So another way of phrasing this first point is that large-scale structure is very powerful, probably more powerful than the CMB, in constraining multi-field models, pinning down the field content during inflation, or at least the fields that determine the initial curvature perturbation. But it can't tell you very much about, say, the self-interactions of a single field during inflation. So you're only sort of seeing part of the story with large-scale structure. There's some degeneracy between models. For example, FNL and GNL are hard to distinguish. But there are a few observables that let you discriminate models. And the observables that we think are important are the spectral index of the bias and the question of whether the bias is stochastic or non-stochastic. All right, so just to summarize, there are, so I've surveyed a variety of endpoint signals that one can look for that tell you different things about inflation. The CMB data analysis is sort of ideal in that the CMB is linear, so it takes an endpoint function to an endpoint function. And so you can differentiate, say, a 3-point signal from a 4-point signal. You have roughly the same configuration discrimination in the CMB as you do in the 3D curvature perturbation itself. So the mantra here is sort of one for each diagram, for each Feynman diagram, or for each interaction that you're interested in, one can write down a different estimator and have full shape discrimination. So the CMB has been very powerful, but unfortunately we're close to maxing it out with Planck. Large-scale structure is a really interesting future frontier that I think all of us should be interested in. This large-scale bias is probably not the whole story, so that's an interesting thing to talk about, but it's subject for a different talk. So future constraints should eventually beat the CMB, but it's only really been demonstrated, at least, that this happens for models with large squeeze and collapse limits, and these are the multi-field models. There's less discrimination than the CMB. It's hard to separate different shapes of the endpoint function. You really just see the scaling, the overall scaling in some squeeze or collapse limits. Even different values of n, FNL, which is a 3-point signal, is hard to differentiate from GNL, a 4-point signal. But there's some scope for model discrimination based on spectral index of the halo bias and stochastic versus non-stochastic bias. Thanks.
If I could make a comment about large structure in the 3-point function, because we know that the 3-point function is the optimal way to see non-Gaussianities. Even for the local shape you talked about, there is a signal in the bias. We do the bias because we are not good with the 3-point function. But if you forecast the limits you get with the 3-point function, it's already a factor of 10 better than what you get from the scale-dependent bias. And the same is for, and it's even more for FNL equilateral, orthogonal, and all the other ones that come from single-field inflation. I think the 3-point function has been undervalued. Nobody cared in large structure, but I think I would like to urge the community to think about that, because the forecast, if you just count the number of modes, they're very good. And we're going to measure those modes. So I just wanted to.
Yeah, I totally agree with your comment. I sort of hinted at it during the talk, but I didn't really talk about it. Yeah, I think the three-point function of large-scale structure, it's really understudied. Like no one has, there's scattered results in the literature, but no one has demonstrated, even in the Gaussian case, that there's a model of the three-point function that fits, say the three-point function of halos, that fits at the level of, you know, a reduced chi-squared of order 1, n-body simulations out to some modest scale, like say 0.1 inverse megaparsecs. So I view, I mean, there's some interesting papers that, that I would convince me, at least, that the three-point function is probably more powerful. I mean, I think I agree with you that the three-point function is, it's been convincingly shown is more powerful than the two-point function. But no one's really taken this to the level of working out all of the analysis issues that you would need to put in, even just like an ideal n-body simulation, spitting out an FNL, marginalizing over all the bias-like parameters, second-order biases and so on you need to marginalize. And then just demonstrating that that estimator has a scatter that matches the forecast. So I sort of view that as work in progress, but you know, a really interesting thing that we should all be thinking about.
All right, one more question, and Dan, could you come down? Any question? Well, what about the spectral distortions in FNL? You say the CMB has no legs left, but I thought we just heard spectral distortion could be.
Oh yeah, that's right, that's right.
Yeah.
I mean, for a scale invariant FNL, I imagine it's hard to you know, be competitive with other probes, but I think the point is that it measures triangles with very different scales. It measures the squeeze triangles where where the small k is, say, a Hubble scale, and the two large k's are you know, order 20 U-foldings different. And so one should perhaps think of that as measuring a different, because it measures such a different k range, different observable than the FNL that we see in the CMB.
All right. Well, let's thank Kendrick.